Hope my screen is visible.
Yes, sir.
Now you can start our discussions. We can start our class. So again, the task scheduling part. So this thing already we have discussed. So quickly going through. So this for parallel machines, tasks and processor. So the task execution time and processor don't vary. So in identical machines, and in uniform machines, machine with speed difference, the tasks vary with speed. Okay, so speed 1, speed 2 by 3, speed 1 by 2, speed 2 by 5. So based on the speed, task execution time differs on different machines. And unrelated means completely heterogeneous. So different execution time of tasks on different processor, but there is no correlations. Okay, so that is, and this thing already we have discussed classification of scheduling problem. So we divide the all classification into using these specifications. So alpha, beta, gamma specifications, and alpha specify the machine environment, beta specify the job, and gamma specify the what kind of objective functions we want to optimize, minimize, or maximize. And this thing already you have seen. So this is what is this? Can someone see? So PM CMax.
Sir, M number of identical processors.
Yeah.
And we want to minimize the completion time.
Overall completion.
Okay.
Okay, and taxes and processor. By default, in this whole courses, most of the time we use the number of taxes whenever we say it is small n, and number of processor is small m. So m processor and n taxes. Okay, and this is execution time. So T1, T2, T3. Sometimes we use PI. Okay, and this problem is NP complete problem. So this is map this problem to M subset some problem. So and it can be mapped to independent set problem. So this is a NP complete in strong sense. So divide the taxes in M set so that difference of sum of execution time of all the set is minimized. So do not exceed the value of k. So this is minimization of maximum of sum set 1, sum set 2 up to sum set m. So we need to divide n numbers or n taxes into m different sets. So this is a well-known problem. Okay, and it is NP complete problem. So whenever we allow, so PMTN, so suppose preemption is allowed. Whenever you allow the preemption, suppose n taxes, m processor, and infinite preemption is allowed. Means preemption is allowed by default, we say. So whenever you allow preemption, then this problem is very simple problem. Okay, this problem can be solved polynomially very easily. So how to solve? So divide all the work among all the cores equally. So let's suppose average of this execution time T1, T2, T3, and Tn. So what do you do? This T1, T2, T3, Tn, sum it up and then get average. Okay, so summation of Ti by m. So this much work you give to each core because preemption is allowed. We can divide the numbers. Okay, and that is the average amount of work every core will do. And another thing is you need to look at the boundary cases. Particularly, suppose a task Ti is greater than means any taxes. Suppose any taxes execution time is greater than average, then definitely Cmax will be average because tasks need to execute serially. We cannot execute a task part of the task on multiple processor at the same time. Tasks need to get executed serially. So that's why Ti, suppose Ti is greater than average, then Cmax will be average. So is this clear?
Sir, how it will be equal to average? How Cmax equal to average?
How?
How we are getting Cmax equal to average if Ti is greater than average?
No, not Cmax is equal to average. It will be Cmax equal to Ti, so not average. So this will be Cmax will be Ti. Suppose there are let's give me examples, so it's better. Suppose one task is execution time is suppose T1 is equal to 10, T2 is equal to suppose 3, and T3 is equal to suppose 4, and what will be average? Suppose 3 taxes and 2 processor. So suppose 2 processor, suppose P1 and P2. So what will be average? So 10 plus 3 plus 4.
8.5.
So it will be how much? So by
17.
2.
8.5. 17 by 3.
So 8 plus 4 is 14 plus 3, 17. 17 by 2 is 8.5.
17 by 3.
It's around 5.6.
No, I am taking 2 processor. I am taking 2 processor P1 and P2. So in that case, 8.5. But one taxes is this average. Average is equal to 8.5, but one taxes T1 is greater than average. Whenever T1 is any taxes, okay, any taxes is greater than average, then Cmax will be average. Yeah, Cmax will be T1 in this case. It cannot be average. So this is my mistake. So in this case, if Ti is greater than average, then Cmax will be Ti. For any Ti, if it is greater than average, then it need to be Cmax equal to Ti, because tasks need to execute serially. So thanks for pointing out this mistake. So this is my mistake. And similarly, we need to, what I can say, go for the all the taxes. If after doing the thing, if again the same thing occurs, okay, then it can be done very polynomial time. This is a very easy problem. Okay, it is clear.
Yes, sir.
There should not be any issue. This can be solved very easily because you are allowing preemptions. Because of the preemptions, so you divide the work among all the core. Okay, so this is a very simplistic way, and it will definitely give you the optimal. And only boundary cases you need to handle if any taxes is execution time is greater than average, then Cmax will be average. Okay. And what do you need to do? Any taxes for any taxes. Not only that, one more thing we need to look at is whichever is maximum one. So suppose take the maximum Ti and average it. Okay, so what is maximum Ti? What I was saying. So maximum of Ti, all the Ti, maximum of all the Ti, if that is greater than average, then only you need to do. Okay, and you need to do recursively for that thing. That's why I'm saying handle the boundary cases. So that boundary cases come on what this kind of cases arises. Suppose not one taxes, there may be 2 taxes which is more than average. Then which taxes we need to take? Are you getting a point? Suppose 2 taxes is having more than average, then which taxes to take? The maximum execution time taxes. Let's move to another problem. So what is this problem? QM, PTMN, PMTN, and Cmax. What is the problem? So previous case it is PM, and now we have changed to QM. So what is this problem?
M uniform processors and
So
preemption is allowed.
Preemption is allowed on, we know all execution times beforehand. That means all tasks arrive at time 0. So no deadline business. Okay. And all execution times are arbitrary. Okay. So earlier similar case. So n taxes, M uniform processor, infinite preemption is allowed. And this problem also can be solved polynomially. So simple how to do longer tasks execute on high speed processor till the execution is long enough as compared to others. So what we are saying, one term. So longer tasks executed on high speed processor till its execution is long enough as compared to others. Suppose you take a longest task, try to assign to the highest speed processor. Okay, and you assign that thing till as long as it is long enough as compared to other tasks. Okay, so how we can do that thing? So sort tasks based on the LPT. What is LPT? Longest processing time. So we need to consider the longer task first, then next longer, then next longer. and allocate the long taxes to higher speed processor one by one. When execution time of longer task is no longer long as compared to other taxes, then co-executes. So what I'm saying, co-executes. Okay, so this
Excuse me, sir.
yeah.
So is it like LRTF, like all the long processes will be scheduled first, and then when they have equal time burst time, then all will be done parallel
No.
one by one?
So let me explain you. So suppose let me go to this examples. Suppose you have 5 taxes. So this is one examples. So suppose you have 5 taxes. Okay. So this is the execution time. This one is this one. Are you able to see the graph?
Yes, sir.
So this is there are suppose 5 taxes: P1, P2, P3, P4, and P5. And clearly in this case, P1T is greater than equal to P2T. This is longer taxes wise you have sorted. Okay, so P3T and so on. So here 5 taxes. P1 have higher execution time, longer taxes. P2 have next longer. P3 is next longer. P4 is next longer, and P5 is next longer. Suppose you have 4 machines. Suppose you have 4 machines. Okay. Suppose 5 taxes and 4 machines. So very for simplistic examples. So what we are trying to give. So M1, M2, M3, and M4. So job one. So job one we are giving to M1. So M1 have higher speed. M2 have next lower, then next lower, then next one. Okay. So M1 is a higher speed machine. So P1 this job one we are electing to M1. Okay. Job one we are allocating to M1. So are you able to see this point? So job one is allocated to M1. Then what we are allocating? Job two we are allocating to machine 2. Okay. And now this job 1 and job 2 got allocated to M1 and M2. But if you look at this point, because M1 is running faster rate, so are you able to see the slope? So this slope, because M1 is faster machines, that's why this effective execution time of job 1 minus remaining executions, it decreases very faster way because M1 is faster machines. So remaining execution time of this shows the remaining execution time of job 1. So this is reducing, and for P2 it is reducing little bit slowly. So at some point remaining execution time of both P1 and P2, that means job 1 and job 2, each at time T2, what is happening? Remaining time of job 1 and job 2 is same, because job 1 is executing at faster rate, so that's why remaining time of job 1 is decreasing faster way, P2 decreasing little bit slowly, and these two things, these two lines is meeting at this point, and this point we are saying as T2. At T2, what we'll do, both job 1 and job 2 will co-execute on M1 and M2 simultaneously. So we'll co-execute J1 and J2 on M1 and M2 simultaneously. Okay, take P3. P1, P2 have allocated. Now P3, you will get P3 got allocated to M3, and this P3 is executing slowly as compared to this job 3 is executing slowly as compared to job 1 and job 2, but it is not meeting any other slope. Because it is not meeting any other slopes and it is finishing at T4, so we don't have any issues. Okay, but whenever we are allocating P4 and P5, okay, 4 machines. So initially P5 is not allocated to any machines. Okay, but P4 got allocated. That's why P4 job 4 got allocated to machine 4, and job 4 time is reducing. At some point, okay, this P4 slope, this is P5, that is job 5 slope, because you are not allocated now, so it will be constant, and this guy is reducing. P4 is reducing, remaining time of job 4 is reducing. At some point T1, because as it is both the slope is meeting, we need to do, so job 4 and job 5 need to co-execute on M4. What we are trying to do? So we are means co-executing job 4 and job 5 together. If the slope meets, then only we need to do the actions. Okay, if the slope don't meet, then we don't need to do. Let executes continuously. Are you getting this point? We are trying to allocate longer tasks onto high-speed machine till the task is longer. Okay, till the task is longer means remaining time is longer. So whatever I state, the term is longer tasks executed on high-speed processor till its execution is long enough as compared to others. So it says this thing. Is this clear?
Sir, what do we mean when we say co-executing? Like regular context switches between the
Yeah.
two machines.
So they will execute on the J1 in this case. In this case, J1 and J2 will execute on M1 and F2 with very infinitesimally very small context time. Okay, context switch time. So they will execute one after another infinitesimally very small. Theoretically, you can say we can co-execute J1 and J2 on M1 and M2. Practically, it might not be possible, but theoretically, you can say. Is this clear?
And sir, J4 and J5 will be scheduled like round robin manner in machine M4.
Yeah, it is practically round robin manner, but whenever we say theoretically, round robin manner with this what you can say time quantum is absolutely zero, almost zero. Whenever we say theoretically, is this clear?
Yes, sir.
Whenever means practically, whenever we say we need to give some time quantum, but whenever we say theoretically, then time quantum may be almost towards zero. That means they will co-execute simultaneously. That also fine. Is this clear?
Yes, sir. And sir, also after merging of P1, P2, their slope would be the average of the initial two slopes.
So whenever in this case we are merging P1, P2 because P1 is means reducing very at larger rate. P2 is reducing a little bit lower as compared to P1. That's why it is merging. Once it is merged, then only you are doing co-executing. So now we can say remaining time of both job 1 and job 2 will be executing on M1 and M2 together with average speed with two machines. Are you getting a point? This fine.
Yes, sir.
Okay, so and this algorithm will give you optimal result. It is proved to be optimal. Okay, so how to calculate this timing, particularly find the how this is reducing. P1 is reducing with speed something, and you need to calculate the slope. We need to calculate this point T1, T2, T3, and T4 points. These are the points we need to calculate. Okay, so statically it can be calculated. Given all the taxes, this T1, T2, T3, T4, T5 can be statically calculated because all the taxes are given, all the machine speed are given, all the taxes are at time 0. We can calculate statically everything. Hello?
Yes, sir. And sir, like for the combined slope of P4 and P5, so P3 by change of parameters.
Because P3, we have allocating job 3, we are allocating to M3, and it is not meeting any other slope or any other guys execution time.
Yes, sir.
If it is not meeting, there is no issue.
Okay.
If it is meeting, then they need to co-execute.
Okay.
If it is not meeting, there is no issue because it is going in its own way. It is not actually what I can say interfering with others. Okay, so the same thing. So what we are trying to, I'm going back to slides and trying to look at this level, particularly this this leveling, particularly T1, T2, T3, T4, and T5. This leveling we are trying to get. Okay, so this is called get the level. Okay, so algorithm level. So while there exists a job with positive level, assign T. So what we are trying to do? So T1 minimum S and T, a job completed time S, and another thing is minimum S and T. There are jobs I and J where PIT and PIJ with initial PIT, okay, is greater than PJT, and this is remaining time. Okay, remaining time at S. Remaining time at S. Okay, this is T2. Remaining time at S. Then what we are trying to do? We are getting a intersection point, and we are calculating the intersection point. Okay, so we are calculating the intersection point. So PS, S is the whenever remaining time of PIS and remaining time of PJS at time S. If they're equal, earlier it was not equal, one is higher and other is lower, and at S it is equal, then we need to look at that point. Okay, among this T1 and T2, we need to like pick the minimum point. So that we are calculating, and once it is equal, then we need to co-execute. So in this case, so earlier P1T is greater than P2T, but at time T2, or this is suppose S is T2, at this point, both are equal. Remaining time of P1T and remaining time of that is P1S or P1T2. So what I'm saying is P1T2 equal to P2T2. So P2T2. So at this point, remaining time of both those guys are same. So that we are trying to say, and we are marking that points. That is algorithmic level we are saying. And once you have done that thing, then you do these things. So from level, look at the level and where you need to execute co-executes, the co-execute, otherwise execute separately. So this algorithm is nothing but writing the things in a textual way and a formal way. But what the meaning is this. Okay. So how to calculate and how to do these things. Is this clear? Any questions? And this slide actually I have taken from Brooker book. Okay.
Sir, what is the units of P1 of T? Is it the execution time which is remaining?
Yeah. So P1T is actually execution time.
Okay, so the units of slope is dimensionless.
Time unit. You can say time unit, not second, not minute, but it is time unit. You see.
Okay, sir. And the unit of slope is it dimensionless?
Slope means suppose in this case, suppose P1T. So P1T means job 1 is assigned to the faster machines. As job 1 is assigned to faster machines, initial time is P1T, but after some time it will reduce. Because it is assigned to faster machines, the remaining time, okay, will reduce in a faster way. Remaining time will reduce in a faster way, and this slope represent the remaining time is reducing at faster way. This slope is little bit slower as compared to this slope. Okay, and this in this case P5, we will get job 5. We have not assigned till this point. That means this slope is not reducing. Okay, means the execution time is remaining execution time is not reducing.
Okay, sir. And one more thing, how do we measure the rate of execution time of a machine? Like how fast is a task running? What are the units for that?
The problem is in the problem speed of processor is given. So what we are assuming is speed of processor is given.
Okay, so speed of processor is measured in?
We can say measured in what I can say frequency, not but we can say gigahertz or megahertz, we say. But in critical point of view, it is given, speed is given. So higher the speed, execution time will be lesser.
Okay, sir. Thank you.
Two numbers is given. Okay, speed is given in term of number.
Yes, yes.
So basically theoretically, we are not looking at exactly which machine, what is gigahertz and this thing, but we are looking at number point of view, algorithmic point of view. It is fine.
Yes, sir, it's clear now, sir.
Yes, sir.
Yeah. Then next we'll move towards other things. So in precedence constant, whenever you say precedence constant or DAG, so general term let's discuss. So before, what is precedence constant? Precedence means job need to execute before some job. If precedence constant is there, so before certain jobs are allowed to start processing, one or more jobs first have to complete it. So if dependency is there, so if suppose this is the dependency, so if you look at this J9, so J9 need to be means started after completion of J10, J11, and J12 because J9 have dependency J10, J11, and J12. So that's why you call it is successor. Okay, then predecessors. So predecessor means after J9, then only it can complete J7. So J7 it gets predecessor. So in a graph theory we read this thing, so we don't need to go and discuss. And what is immediate successors and immediate predecessors? So just this is immediate successor and immediate predecessor, and transitive relations. One or more job have to finish arbitrary. What I can say acyclic graphs. So we're not going to discuss this successor predecessor anyhow. We know and say in our basic discrete math course. Okay. So what are the special constant? Special precedence constant. So in general, precedence constant by default we say DAG. That is the or peak or DAG. That is the biggest one. Biggest one means what you consider in most of the cases. Other are in tree, in forest, opposing forest, interval order, series parallel order, and level order. So we'll not go per interval order, series parallel order, and level graphs. Then let's see what is in tree, out tree, opposing forest, organ join. So let's see with the examples. So that it will be more clear. What is in tree? So this is in tree. So this one is in tree. So this is in tree. So for a particular node, okay. So all are in and then outgoing. So this is in tree. This is opposing forest. This is opposing forest. This is out tree. This is out tree. So in binary tree, what happens? So if you look at binary tree. So binary tree. So every node have two outgoing node. So suppose what will be binary tree? So this will be what? Binary out tree. This will be binary out tree. This is binary out tree. If this is example. Okay. So this is out tree. Whenever it's a by default binary tree, then binary out tree we say. Okay. So this is out tree. This is in tree. Okay. So this may be not only one, that may be many such things. So this is in forest, in tree forest, and this is out tree forest. Okay. So this is a convention we use. Okay. So this is very not difficult because in discrete math course also we read this thing. Okay. So what is in tree, what is out tree, and what is in forest and out forest, and what is opposing forest? Opposing forest means a combination of both in and out in one forest. Okay. And there is another problem. Suppose there is a problem PM, preg, Pj is equal to 1, and Cmax. What is this problem? Can you please someone tell what is this problem? What problem we are saying? So PM, preg, Pj is equal to 1, Cmax. What is the problem?
We have m identical processors, and there is a precedence constraints given. Each process has execution time of 1 unit, and we have to minimize the overall execution time.
Yeah. So clearly, job characteristics in this case. So this is precedence constant. So by default, whenever it's a precedence constant, it is a DAG. Okay. So DAG, directed acyclic graph, and preemption is not allowed. And release time of all job is 0. So if it is not given, then by default 0. And if it is not given anything, then deadline is equal to infinite. Okay, DJ is equal to infinite, and M identical processor in this case. And what most important thing is PJ is equal to 1. Execution time of all the job is unit execution time. Okay, so this is the thing. And what we are optimizing? Cmax. optimizing in this case means, in this case, we are minimizing the Cmax. Cmax means the last time of the time of last finish executions, last job finish executions, and Cj denotes the finishing time of job J in schedule S. So what we are trying to Cmax is equal to max 1, 2, and Cj. So this is completion time of job J, and we are trying to minimize the Cmax. Okay, so this is this tasks are arranged in a DAG format, general precedence, and all execution time of tasks are each unit executions. Preemption is not allowed. Okay, and M identical processor. So can you say means how to solve this problem? So is this a difficult problem? By looking at the problem, can anyone say or just infer or something or give some suggestion or guess?
Uh, Sir, like I am thinking if we have adequate number of processors, then in that case it would be just equal to the diameter of the dial, the longest path.
Longest path is fine, but sometimes your Cmax will be definitely Cmax will be not less than the diameter. That is fine.
Sir, maybe
Yes.
we can do topological sort, and each independent path we can give it to a different processor.
No, that also will not work. Suppose you have even if sufficient number of processor is there, if sufficient M is very high, then whatever Tanvi say that Cmax will be critical path. Okay, if M is very high. Okay, so suppose what I can say M is greater than much greater than N. Okay, so we have enough number of processor. So number of tasks is N and M is number of processor, and M is M is larger than N. Then you can say definitely on this Cmax will be the critical path. Critical path means what is the diameter. Okay, so that is fine. Okay, but for general case, what will happen? So this problem is proved to be NP complete. So this problem is proved to be NP complete. So we'll see that thing. And for what cases it is not NP complete, and what are the approximation we can think. And these kind of things are available in our Corman book. Okay, so Corman and recession book. So let's see once other things, and then we'll come back to this problem again. Okay, so what is a Gantt chart? In OS book, we have read about the Gantt chart. So Gantt chart indicates the time each job spent in executions as well as the processor on which it executes. So Gantt charts, it describes the allocation, also it allocates the scheduling. Okay, so what is Gantt chart? So we have read in OS book. OS course we have read this thing. Gantt chart means it indicates the time each job spent in executions as well as the processor on which it executes. It is what we are saying is for some schedule. So this is the what I can say, this is a task. This one is task environment. So this is a task environment, and we have around 15 jobs arranged in some DAG format. And this is 3 processor. We have to execute on 3 processor, and we're showing some Gantt chart. So here it is optimal or not, we are not saying, but we are showing some schedule and just giving some example of Gantt chart. Okay, so nothing else. So, and the main motivation of giving this figure is what is Gantt chart? Gantt chart indicate each job span in executions at what time it executes on what processor. That means it define both allocation and scheduling, allocation, binding, and scheduling. So is this clear? Gantt charts, it have how many processor, which tasks or which job get executed on which processor at what time. Everything we'll see in Gantt chart. Is this fine? What I'm saying is what is Gantt chart? How we are scheduling, what is the optimal schedule we are not looking at. So this is example, this right hand side, this task set we are scheduling on this 3 processor and showing the Gantt chart. Okay, it is clear.
Yes.
Okay, so this is what we are trying to say. What is Gantt chart we are saying. So in our OS course in general, we have seen the Gantt chart for single processor. Okay, but now we need to look at Gantt chart for multiple processor. Okay, and sometimes the Gantt chart looks very big. So whenever the number of processor process 3000 or 4000. So even if this table, okay, this two-dimensional table storing is very difficult for more than 3000 processor or 4000 processor, and our number of taxes are very huge. Maybe 10 million taxes and 3000 processor or 5000 processor. So sometimes we need to use proper database or Oracle kind of database or MySQL database to store the Gantt chart system. But at least we should know what is Gantt chart and how we represent the Gantt chart. So this thing, whatever we have told you, so this PM, PREC, PG is equal to 1 CMAX. This problem already we have discussed. Okay, so this problem is proved to be NP complete. So M identical machines, tasks are arranged in general precedence or DAG format. Execution time of all tasks is 1. And what we want to optimize? CMAX. Okay, so minimize the overall execution time. And this problem is proved to be NP complete. And it is proved by Ullman in 76 and Langston in 78. So this map to 3 side and this is click. We are not going and proving this thing again. Okay, so this is proof is out of syllabus. So this is not theory courses. So morely we'll look at from the very high level point of view. So this problem is NP complete problem. Okay, so whenever if something is NP complete, then what do we think? In general, we think of either approximation or heuristics. Okay, so this is specified another kind of problem. So if general precedence, if it is a suppose this task graph is not DAG but is a series parallel graph. What is series parallel graph? So this kind of graph, right side are able to see series parallel graph. Kind of this is still DAG. Okay, still DAG, but it has some pattern. Still DAG, but it is some pattern. Okay, it is a DAG, but it is a specialized version of DAG, series parallel graph. So it starts with the forking, then again it executes for some time, again it joins, and again it starts. So for series parallel graph also it is NP complete. For opposing forest web, what I am saying, opposing forest also it is NP complete problem. So general DAG, specialized version of DAG, that is series parallel, and opposing forest is NP complete problem. Again, proof is out of syllabus. It is fine. So what I'm saying the statement. Okay, I'm not doing the proof. Okay, at least we should understand what is series parallel graph and what is opposing forest. So I've defined tree. Okay. And let's go for any algorithm. Suppose you take this problem. So this problem. Okay, and what is the best way we can think of approximation algorithm or any algorithm? So there is a standard algorithm people says that is called critical path algorithm. Okay, CP algorithm. So that is called who. That scientist name is who, and highest level fast or critical path. So both the same. So in 1961, this is very old concepts. So 40 plus 20, around 60-year-old one. So critical path or highest level path algorithm. So assign a level h to each job. If job has no successor, hj is equal to 1. Otherwise, hj equal to plus 1 plus maximum level its immediate successors. And set up a priority list L, non-increasing order of this job level, and execute the list policy on the levels based on the priority list. That means whichever the maximum level. Okay, so set up a priority list, non-increasing order of job level. So with example, it will be more clear. So this is the textual we were saying. So what is for this examples? So suppose you have 3 machines, M1, M2, and M3, and we have how many jobs in this case? 13 jobs. And clearly, so these are tree. So this is, in this case, it is tree. It is not DAG. but this is a tree in this example. Okay. So the lowest level, so assign job level 1. So J1, J2, J3, J4, J5, J6, and J7, whatever assigning level 1. Then J8 and J9 were assigning level 2, and this J13, J12, J11, and J10, 10, 11, 12, and 13 were assigning level 3. And based on our algorithm, so which taxes we should take first?
Highest level task.
3 level task. Okay, so whatever level 3 we should take first. Okay, so clearly there are 3 levels, 3 level, 2 level, and 1 level. So level 3 taxes, level 2 taxes, and level 1 taxes. This is we have created a list. This one is we have created a list with the level 3, level 2, and level 1, because in this example you have only 3 levels, and you try to assign the highest level first. Okay, so what we are trying to do, J10, this is serially we are doing J10, J11, and J12 we are assigning. Okay, first, then J10, J11, and J12. Okay, so this thing we have assigned. Then we have assigned J13. Okay, so once you finish the J10 and 10, 11, and 12, then only you can go for J9. So J9 here assigned. Okay, so once you finish J13, then only you can go for J8. Okay, so J8. What is J7? Once you finish J9, then only you can execute J7. But in this case, we cannot execute anything, because even if we have one processor is free, we cannot execute anything. Okay, after that, we can execute rest of the things. After that, we can execute rest of the things. So in this way, you can execute. This is an example of critical path algorithm, or highest level first. We are creating levels from the bottom. Okay, so bottom level is 1, then next is 2 level, next is 3 level. So is this clear?
Yes, sir.
Any doubt? Other people, other student?
No, sir.
No, sir.
Okay. So, and this CP algorithm or critical path algorithm. So if you look at time complexity, so we're not going to a detailed analysis, but still order of B plus E. Okay, B is number of jobs and E is number of edges. It is time complexity is because it is in tree format. Okay, and already in 1961, that same guy who already proved that for PM, Pj is equal to 1 for in tree or out tree. In tree or out tree. So this Cmax, whatever it produces, it is optimal. If it is in tree or out tree, so either one. Okay, or in forest or out forest. So for tree, okay, so either it is in tree or out tree, not the mixed one. Okay, so in tree or out tree, or in forest or out forest, either. This CP algorithm or highest level fast algorithm will produce optimal result. If it is a tree format, and what you are saying? Execution time of all tasks is 1. Preemption is not allowed. Okay, preemption is not allowed in this case. Okay, and M processor, if it is tree format, then this HLF algorithm is optimal. This is proved to be optimal. So we are saying the statement, and it is also true for tree, it is optimal. Okay, and if it is not a tree, so general DAG, then if M is equal to 2, so M is equal to 2, then this is 4/3 approximations, and this is easily can be proved. And if M is greater than 3, greater than or equal to, what is M? Number of processor is 2. If number of processor is 2, then 4/3 approximations, 4/3 approximation, and if M is equal to greater than or equal to 3, then this 2 minus 1 by M minus 1. So this one is better off. So if number of processor is less, then it is coming about 4. What is 4/3? 1.5. three approximations. And this one is suppose m is suppose you make it m is equal to 3. So what will be this? 2 minus 1 by make m is equal to 3. 3 minus 1. What is 3 minus 1? 2. So what will be approximations? 1 by 2. So this one will be 1 by 2. So this is 1.5. If m is equal to 3, then it can go up to 1.5 approximations. And if m is equal to 10, m is equal to 2, then it can go up to 1.33 approximations. So which one is better? So m is equal to 2, 1.33. So for m is equal to 2 cases, it's go up to 1.3 approximations. And for m is equal to 3, it can go up to 1.5. Suppose m is equal to 5. If you put m is equal to 5, then what will happen? Suppose m is equal to 5. So 2 minus 1 by 5 minus 1. So what is 5 minus 1? 4. 1 by 4. That means 1.75. Whenever the number of processor increases, it actually approximations actually means increases. Okay, so culturally 1.333, then 1.5, then suppose for 5 cases 1.75. Okay, so whenever 2, 3, 5, whenever you increase the processor, then this approximation ratio also it is increasing, and it can go up to 2. Is this clear? So what I'm saying is means who are not proving the things, whatever the already got result, that thing we are showing. Okay. And let's look at very simplistic examples. So PTS for PM, PREC, residence constant, PG is equal to 1 and Cmax. So polynomial time approximation. So very simplistic approximation. So simple greedy scheduling or list scheduling. So this will be discussed, and okay, it will be discussed. So it is available in our CLR book, chapter number 27 in multi-threaded algorithm sections, and we'll discuss about HLF and MSF algorithm. But it's highest level fast, most successor fast. These are the again heuristics. Okay, so these are not proved one, but this one is approximations. Okay, so list scheduling policy. So very basically, we create a list. Okay, set up the priority list L, and when a predecessor processor is idle, assign the first ready task to the processor and remove it from the list. So whatever we have seen in the earlier case. So this is nothing but same thing as HLF. Okay, so this is Pu algorithm. So what we are trying to do, so we are trying to do the same thing. So in earlier case, what we did this case. So create a level based on level 3, level 2, and level 1. Based on that you do, and if a processor is free, then assign it, or if a task is free and processor is free, then assign it. So this is what we are trying to. J11 we are assigning, J10 we are assigning, J12, and similarly we are trying to do. And first job of the list may not be ready. So something. So whenever in your list may not be ready. May not be ready means if its predecessor is not finished, then we cannot execute. Okay. And Graham's list algorithm, very simplistic, and it is again 2 minus 1 by m approximations. Okay, so similar to whatever earlier. In this case, 2 minus 1 by m minus 1 it is there, but it is 2 minus 1 by m approximations. So this is very simplistic. What is the list scheduling? So list scheduling algorithm, which arbitrary job list is called Graham list scheduling. So what we looked at is for independent job also we'll try to see. So let's look at how this Graham list scheduling people do. Okay, so in your Corman book, so you have heard about this book, na Corman book, algorithm Corman book. Hello.
Yes, sir.
So algorithm Corman book, what it gives actually. So this they try to solve this problem using approximations. So what is this problem? Again, same thing. M processor
Sir,
is equal to 1. Yeah.
what if the list before there is an arbitrary list, right? So what if that list doesn't leads to any execution order, like due to some precedence constraints or so?
We need to maintain the precedence constraints. So in this case, we mentioned the are able to see first job of the list may not be ready. What ready means? if its all predecessors have executed, then only it will be ready. Is clear?
Yeah, but list can be formed arbitrarily, like so all the level 0 jobs, if they are given at first in the list, then it's not possible for any execution order.
But whenever you are assigning the job, so once the earlier job, all these predecessors finish, then only you can execute. So after creation of the list also, the job, first job of the list, whatever the first may not be ready, or some jobs of the list may not be ready. Okay, so only ready job can be given, but in the order. It's fine. Okay, so this is a standard. I have taken from the standard text, so this is nothing to worry. So you can go and read this thing from your algorithm book. Suppose there is a DAG. Okay, so there is a general precedence constant. All the tasks execution time Pj is equal to 1. So in this case, all execution time of tasks is 1. And this term also we have used TP, execution time on P processor. So this term also we have used earlier. So suppose you want to execute on P processor. Okay, so suppose in this case we are saying P processor. So TP is execution time on P processor. Okay, so T1 is work. How many work? Suppose in this case, how many nodes are there? If you look at how many nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Some 18 nodes are there. So in this case, how many work are there? So if T1 is equal to total number of nodes. And what is T infinite? Suppose T infinite means suppose you have infinite number of processor. Okay, so Tanvesh, can you correlate? So suppose you have M is very large, number of processor is very large, then N, then it will be the critical path. So T infinite is span, also called critical path length or computational depth. So we can say critical path length or computational depth or span. So, and if you have infinite processor, suppose more number of processor, can I say, so these things TP, time on P processor is always greater than total work by P. P means number of processor. Can I say this thing? TP is always greater than equal to T1 by P. Hello?
Yes, sir, as long as there is some kind of precedence.
Yeah. So even if not precedence, still I can say.
Yes, sir, equality will hold.
Even if there is no precedence, still I can say. Okay. And can I say TP is always greater than T infinite? Greater than equal to? It cannot be lower than T infinite because that is the critical path. Whatever number of processor you take, TP must be greater than equal to T infinite, greater than critical path. It cannot be lower than critical path. Tasks on P processor cannot be lower than the critical path. Okay, so clearly, so if you look at this thing, so what is the in this case critical path? So in this case, if you look at the critical path, is this one is critical path. So are you able to see the critical path? So this guy, 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 and this guy. So critical path is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm giving whatever number of processor, you cannot finish between 9 unit of time. Definitely it will take 9 unit of time. Is this clear? Because critical path, that is the critical path. Longest path. So whatever you say diameter, so here also same thing, longest path. So longest path is it will take time. Definitely TP or execution time on preprocessor will be definitely be not lesser than the critical path. Okay, so what we are trying to say is actually we're trying to say this Graham's this algorithm. Okay, the greedy scheduler, suppose you choose what is greedy. So whenever a task is ready and a processor is free, then give the task to processor. That is a greedy scheduler. Okay, so what I'm trying to do, so whenever a task is ready and a processor is free, just give the task to that processor. So whenever, so can I say that TP is less than equal to T1?
자기 왔어. 왔어.
Can I say
나 아무도 수행시람.
we're getting some noise? Okay, can I say that T1 by means TP is always less than this is what T1 by P plus T infinity. This is the critical path, and this is the work by total number of processor. And TP will be always less than the work divided by processor plus critical path. So in which we are trying to say is whenever you are scheduling the tasks on M processor, suppose in this case P is equal to 3. So at any point of time, so complete step means number of complete step is less than T1 by P. Since means what is complete step? That means here all the processor are busy. Complete step means all the processor are busy. So you have enough tasks to execute at a particular state. That is called complete state. And other is incomplete state means you don't have enough tasks to execute the task means on processor. Okay, enough ready tasks. You have more number of processor, but you don't have ready tasks. So number of complete tasks. This is number of complete tasks. Complete step is less than T1 by P, because suppose all are independent. Suppose all tasks are independent, then still this thing will hold. Since each complete step perform P work. Suppose all are independent tasks, then this will definitely make sense. Okay, so number of complete state will be T1 by Tp, even if no precedence notion, all are independent tasks of unit execution time. And next one is incomplete state. Incomplete state is always less than T infinite, because there is a critical path. Okay, at any point of time, because there is a critical path. Okay, so number of incomplete step will be less than T infinite, since each incomplete step reduces span by 1 unit. Because of these two regions, so this TP is less than equal to this. One is number of complete step, and another is number of incomplete step. Okay, because TP is less than T1 plus P plus T infinite. So what we can say is TP will be always less than number of complete step plus number of incomplete step. Okay, so this is actually critical path. This one is critical path. If you see the animations, this is the critical path. Okay, so this is incomplete state. And in this case, what we are saying is this one is, are you able to see the animations? If you look at the animations, so we have 3 processor and all the 3 processor is getting ready tasks. Okay. And we can directly say, if suppose TP is already time is up, I think. So we can discuss this in the next class maybe. Okay. So, and this thing I have taken from your algorithm book. This I have taken from algorithm book. Okay. And we can also go and read to this book. You have any questions? This thing we'll discuss one more time because time is up. Hello? Yeah, Tanvish, please tell.
Sir, when we are doing all these heuristic algorithms, so these would be applicable if only if all the uh, processor execution time is same.
Yeah, so in this case, we are solving the problem. So actually, this problem we are solving. So we are solving the problem, this one. We are not looking at other problem. So PM, Pj is equal to 1, right? So all the execution time is 1. For this case, we are trying to solve. And even for this problem is also NP-complete problem. So why not to look at a simpler version? In our Corman book also, it gives the first simpler versions. Then only we'll go for the Pj is arbitrary. You got my point?
Yes, sir.
For independent job, so we'll try to go for arbitrary first. Okay. So suppose no precedence, only independent job. All are independent job, and Pj is equal to arbitrary. So in that case, because we know this problem also, this PM, then Cmax. This problem also NP complete problem. Why not to go for heuristic for that, or any approximation for that? That also we looked at. But in this case, we have precedence, but all execution time is 1. We're solving this one. Okay, if you don't have any questions, then we can.
Hello, sir.
Yeah.
Sir, in list-based scheduling, why should we take the node which is longest from sync?
Why we take that in list based? We are trying to create a list. So in this case, if you look at why we are taking this thing, so we are creating CP algorithm. So this who critical algorithm it takes in this way. Otherwise, we can go for other variety, most successful paths or on any other varieties also we can see. But this is HLF or CP algorithm is proved to be optimal for tree. Is optimal for tree and not for DAG. And in this case, it takes from the as a critical path algorithm. So it start from the last node, sync nodes. We can go for not for other node, but it may not. We cannot prove or we cannot. We can make it a heuristics. But at least for HLF or CP algorithm or WHO algorithms, if it takes from the bottom, then it can be proved to be optimal for at least 3. Is this clear?
Yes, sir.
Yeah. Okay, so any other questions? Okay, so if there is no question, then I'm stopping.